All right, everybody, so we're back for part 2 of Module 10. We're talking all about the universe this week and how it relates to biological evolution. So hopefully this PowerPoint presentation doesn't go too long. I apologize in advance, it might be a little bit lengthy. There are quite a few slides. So bear with me and hopefully you all find it interesting. All right, so just a reminder for the new assignments that were assigned earlier this week. We have our Module 10 quiz. Make sure you guys take your Module 10 quiz by Tuesday, April 21st. Those 10 random questions are open book. Also on our list here, make sure you watch your universe video that I supplied via email and also on Cobra. So if you have a hard time getting that to download, just let me know. It is on YouTube, so hopefully you all aren't having any issues with YouTube. So as long as YouTube is working for you, this video should work for you. This is in replacement for our planetarium visit for our lab. So make sure you watch it. It is really interesting. And then lastly here, I want you all to be working on your PowerPoint presentations that are due on April 21st. That is your 3 to 5 minute presentation that you have to do for me. And it is for quite a few points, so make sure you're doing that and that you're spending a fair amount of time on it. That is in replacement for our lab that we had to do this week. So that's essentially your lab assignment. So make sure you're doing that. I don't want you guys to lose any points. So those are your 3 assignments for this week. And we're going to get right into our Module 10 Part 2. So the first part, we covered the 4 sections: the night sky, the origin of stars, the brightness of stars, and star temperature. Today we're going to be covering star types, the life of a star, and galaxies. I accidentally excluded the galaxies portion on the last presentation, but that is the 7th section. And then the next lesson here, we're going to go over the origin of the universe, which hopefully will not be as lengthy. Make sure you're doing your reading, page 166 to 196. It seems like there are 2 different sections. There's one that is a pretty lengthy read on the origin of the universe, and then there's one that's more similar to what you have been experiencing for the last couple modules where it's broken down into sections. So make sure you're doing them both, just so that you're prepared for our quiz on Tuesday. Okay, so we were talking about how to classify a star, how to classify stars based on their temperature categories and what the sequence was. So if you remember from the last presentation I did, there were a few different classes for different stars: the O, the B, the A, the F, the G, the K, and the M, all the way from the hottest to the coolest in temperature and what color they appeared in the sky. And so if we remember that star temperatures were classed by categories and their conventional colors here, it will help us talk a little bit more about the star types that we're going to be discussing in the next few slides here. So first, let me take it back a second and talk a little bit about who the founders of star types were. So there were 2 guys originally in 1910. We have Ejnar Hertzsprung. So he was out of Denmark, and we also have Henry Russell, who was out of the United States. And both of these fellows here in 1910 independently developed a scheme to classify stars. So the same year, these 2 scientists came up with this classification scheme. And the whole scheme was a temperature luminosity graph. So it plotted stars based on their temperature and their brightness or their luminosity, essentially. So they did develop a graph in order to chart the stars, and it was named after both of these scientists here. So it ended up being called the Hertzsprung-Russell diagram. And it's also known as the HR diagram for short. So if I reference the HR diagram, this is what I'm talking about here. So as I mentioned, this particular diagram or this classification scheme, they plotted the stars based on temperature, indicated by the lumosity or spectral types here. This includes the true brightness by absolute magnitude. So if you look at the diagram here, you can see that there's a band that runs from the left portion, the left upper portion, I suppose, down to the lower right portion. So this is called our main sequence. And so we'll talk a little bit about the main sequence here in a second. But you can also see that there are some outliers of stars, and those include the blue giants and the red supergiants and the red regular giants, and then also the white dwarfs. So on either side of that main spectral sequence here, we have these outliers, the giants and the dwarfs. And so those guys are not the norm or the main sequence here for the stars. We see most of our stars falling on that main sequence. And there is a range of them based on how bright they are and what their temperature is. So based on that lumosity and based on the temperature. And the temperature is measured in kelvins. So keep that in the back of your mind as well. We're not talking about any other type of temperature scale here. So our main sequence stars, so as I mentioned, we had that main sequence band that's running from the upper left to the lower right. So that's that band of stars where most of the stars fall along, and the center of these stars are normal mature stars. So the center of this diagram are these normal mature stars, and that's where you see them in the main sequence. So as I mentioned, the upper left, or I guess you have the blue giants and you have the red giants and you have the white dwarfs. But in that main sequence, the upper left of that main sequence here are the most massive of the normal mature stars, and they are the brightest. So those are your blue stars in lumosity, and then also they're very, very high temperature-wise in kelvins. And if you look in that main sequence band on the lower right portion of that main sequence band here, you see the faintest stars, and they're also the smallest. So they have the lowest temperature here in kelvins, but also the lowest lumosity. So that's just kind of how we're going to be reading this HR diagram. Okay, so how do we determine the star's brightness, temperature, and location on the HR diagram? Well, right, they fall a range on this chart, right? So it is actually the mass of the star that's determining where it's going to fall on the HR diagram. So your highest mass stars are going to be your highest temperature and your brightest. So they're going to be on that upper left portion of the HR diagram. Your lowest mass of stars is going to fall on the lower right-hand side of that diagram. So they have the lowest mass, then they have also the coolest temperature, and they're also the dullest or faintest when it comes to brightness or lumosity. And so depending on the mass of the star that we're dealing with here, determines where they fall on this HR diagram, especially in the main sequence along that band of the normal adult stars that we were talking about. So let's do some term time here and define some of our stars that we are talking about. And so I mentioned the red giant stars, and they fell, if you recall, or the red supergiant stars. They fell on the upper left portion of the HR diagram. So these are very bright stars, but they have a low temperature. So that's why they're up higher on the chart, but farther along on the right side. They're very bright, but very cool in temperature. So we also have our white dwarf stars. If you could see on the HR diagram, they were on the lower left portion of the chart. And so those are very faint or very low lumosity, and they are very hot. So very high in temperature, white hot, and then also, but very dull at the same time. So we have our red giants, we have our white dwarfs. And then we also have our variable stars. So these are stars that will change in brightness over a period of time. And so we do have those. That's just important to know that they do exist. And then we also have our Cepheid variables. So these are the bright variable stars that are basically used to measure distances. And so these are just a few terms that you have in your book that are important to know, just as background information, as a definition of what we're talking about here. Okay, and so we're going to be talking about how stars are created. So I find it really funny that a lot of videos, a lot of movies and TV shows are based on the universe or stars. So I found this text in our book about a star being born, and I thought it was ironic to just include the movie that came out, which has is no relation to the universe at all, but I thought I was being clever. Anyway, so the life of the star. So a star goes through several different stages. There are 6 different stages. If you look at stage 5 and 6, you could consider that one stage. So there might only be 5 stages depending on what kind of star you're talking about. So depending on if you're talking about a smaller star or a more massive star. Technically there are 5 stages, but I'm including all 6 here because we have to talk about the end of a less massive star and the end of a more massive star. Anyway, so here are the stages here. So stage 1 is our protostar stage. Stage 2 is our main sequence stage. Stage 3 is our red giant stage. Stage 4 is when our stars go back to the main sequence. Stage 5 is the beginning of the end for our smaller stars or our less massive stars. And stage 6 here is the beginning of the end for our more massive stars. So our big giant massive stars. So you can see kind of I've outlined it here in this image. Basically, this is just the life cycle of a low mass star or a less massive star. So you would see this happening in stage 1 through 5, starting with the protostar stage and ending with the very end here of our star's lifespan. Okay, so we're going to go through all of the stages and just talk about each of them. So stage 1 here, this is our protostar stage. So if you recall from last lecture, we talked about what a protostar is, which is basically all of the gases that are swirling around that eventually become a star due to gravity pulling all of those gases and pieces of the universe together. So that's what essentially is happening here. So gravity is going to start in this protostar stage by pulling all of the gases of the protostar together. So everything's going to be attracted to each other. And eventually, when the conditions are right, nuclear fusion reactions are going to start happening. So we're going to start seeing these reactions happening. And what is going on is these, we're going to have hydrogen nuclei here, 4 of them, forming a helium nucleus. And so this is going to be releasing energy. And this energy is going to increase the temperature, and it's going to expand the volume of the star. So it's going to grow larger over time here. And from the point of when a protostar stage is happening to the next stage, or stage 2, which is our main sequence stage, that's going to take about 50 million years. So it's not a trivial thing that's happening. It's going to take quite a long time for all of this energy and the volume of the star to increase large enough that the main sequence stage is going to be happening. So this is just our protostar stage at stage 1. So our stage 2 in our life cycle of the star here is going to be our main sequence stage. So if you remember the main sequence, that is just that band that falls for a normal adult star along that HR diagram that I showed before, and it ranges, if you recall, from very bright and very hot to very dull and very cool, depending on where it falls along that main sequence. So in our main sequence stage here, this is basically where the star is going to end up on that main sequence band. And that's depending on the mass. Remember, so the mass is determining where it falls on that HR diagram, or depending on how large the star is. So depending on that is where it's going to fall in the main sequence. So our massive stars, our large stars, are going to have a higher core temperature and use up hydrogen more rapidly and shine much more brightly. So that's what's happening when we have a large star. Now, when we have a smaller star or a less massive star, those stars are going to shine at a lower surface temperature and use fuel more slowly. And so depending on what type of star you have, it's going to be your type O or your, for example, all the way through type M. And that is where it falls on that classification scale, if you remember from our very first slide that we talked about here, and also in our last lecture. So for example, if we have a type O star, that's going to be one of our more massive, very hot stars, and that lifespan is only going to last millions of years. And I say only because stars can last for up to trillions of years, which is the case in our type M classification of a star. So because it uses fuel more slowly, it can last a lot longer, and that temperature is a lot cooler, and the star is less massive. And so that lifespan can be upwards of trillions of years, depending on the size and how quickly the fuel is being used. So depending on where it falls in that classification system, depends on how long that star will, quote unquote, survive in the universe. And so I just included a photo of a main sequence star, which is what our sun is. Our sun is in the main sequence star stage. And so that's where it exists on the HR diagram. It's not a supergiant. It's not a white dwarf. It is a main sequence star. Okay, so stage 3, the red giant stage. So I mentioned red giants or red supergiants. Remember, they fall on the upper right portion of the HR diagram, where they're burning very, very brightly and also very, very cool. I'm sorry. Yes, that's correct. Yes, burning very brightly but very cool. Okay. So most of the hydrogen in the core of a red giant has been already fused into helium. So all of those hydrogen atoms that we have been fused into a helium nuclei. There are less reactions happening, and therefore there's less energy being released because there's not as many free hydrogen atoms. They can't be fusing into helium because most of them have already been fused, so there's less reactions happening. And it's at this point where the star begins to start to collapse. So this is where essentially now there is a different brightness and different temperature properties that have happened. And so now we have this red giant. Okay, so the star is starting to collapse. What happens after this red giant stage? So surely the star disappears, right? Well, no. What's going to happen is now the star is going to go back towards the main sequence. So if you have just a common everyday star, it's typical for this common everyday star to spend approximately 500 million years as a red giant. And so after that, 500 million years, now when the star is moving back to the main sequence here, it's having a cooler surface temperature probably about 2,000 kelvins less, so going from 5 or 7,000 down to 3 or 5,000, depending on what the original temperature was. But the helium core here is continually heating, even though this is happening. So you still have a core that's continually heating. And this is going to end up changing the radius, the surface temperature, and the brightness. So because this is all happening, the star is changing back to that main sequence. So it's moving back to that main band that we can see on the HR diagram. And so here you can see in this image, you can see our supergiants, so we can see our red giants. So depending on what ends up happening with a star, it could either be just a regular giant or a supergiant. But eventually it will move back, so it moves from that main sequence to that red giant stage and then back to the main sequence stage. And so this is our stage 4. Now, depending on if the star itself was less massive or more massive will determine stage 5 or stage 6. So stage 5 occurs for less massive stars or smaller stars here. So in the case of a less massive star, we have the core, and that core is gradually being converted into a lump of carbon core after millions of years of reaction. So these reactions have been going on for a very, very long time, and then eventually the reactions will cease and that car will start being converted to carbon. Now the star does have a helium fusing shell surrounded by a second hydrogen fusing shell. So it does have that surrounding the core. And then eventually the star will expand to a red giant for the second time. So it will go back into that red giant stage for that second time before a violent explosion happens and blows off the outer part of the star and only leaves the hot core. So unfortunately it doesn't end well for the star, but eventually it will just leave that outer that inner hot core. And there's a few here. I have a definition here. So that blown off portion of our star, the part of the star that exploded off, is what we refer to as planetary nebula. So that's basically those blown off portions that form just a circular nebula. And then after time here, that remaining carbon core and the helium fused shell will begin to form a very small and dense white dwarf star. So it does have a little bit of life left here, but unfortunately it doesn't fall in the main sequence at all. And so it becomes that white dwarf, and that's where it goes into the white dwarf phase. Now, if we have a more massive star, however, and they have a much different ending than our less massive stars where that explosion is happening. So when we have a massive star, the massive star might go through a carbon fusing stage. So what happens in the carbon fusing stage is when new elements will be produced until you end up with iron at the very end here. And once you end up with iron, the star is basically collapsing and then rebounding, kind of like a slinky or a compressed spring, into a catastrophic reaction, which we call a supernova. And what a supernova is it's a really bright light in the sky. And so there's no collapsing happening in the less massive stars, but that does happen in the more massive stars where it kind of shrinks and collapses and then expands out into that catastrophic reaction. So it does still end for the massive stars essentially, but a little bit more drastic and a little bit more eccentric. So continuing on with stage 6 for the more massive stars here. So at the very end, after the supernova has occurred, the gravitational forces of whatever matter is left of the star, so whatever's left, is enough to essentially force the protons and the electrons into the core of a neutron star. So then that's when we end up with a neutron star here. And so we have a couple other things that are happening as well. We have a pulsar, which is a very strongly magnetized neutron star at the very end of the massive star that emits a uniform series of equally spaced electromagnetic pulses, which is likely how it got its name. And then we also have a black hole, which is essentially a collapsed star that's just so dense that even light cannot escape from it. And then theoretically, a black hole would continue to collapse inward on itself, where it becomes a pinpoint and then a zero radius. So this is what we would call a singularity. And so essentially that black hole would continue folding in on itself and collapsing in on itself, or then it becomes a singularity, which is like basically like a pinprick in the vastness of space here. And so if you were to look at the life of a star here on a map, this is what you might see. So you see our stage 1. Maybe it starts off as a cooler star classified as a G, moves to a 2, and then over to a 3 here, and then becomes maybe like a classification M, and then back over to an F, and then back to a 5. Okay, so then so if you look at 1 and 2, this is falling on your main sequence. Maybe 3 is your red supergiant. 4 is your main sequence again. 5 is when it returns to the red supergiant the second time, and then the very end here is possibly the white dwarf, or what is happening, depending on if it's the end of a more massive star or a less massive star. So this is kind of what you would see, this squiggle of the life cycle of our star here. Okay, so now that we know what sort of life cycle a star goes through, let's talk a little bit about galaxies, which are where stars exist, right? So what is a galaxy, right? Billions and billions of stars that are existing in a galaxy. And this is forming the basic unit of the universe. And so it's all of these billions of stars existing in this place in which we can determine as a galaxy. So we ourselves and our sun and Earth and all of our solar system here, all of our planets in our solar system surrounding our sun exist in a galaxy. It's a very large galaxy, and so it has a name, and it is called the Milky Way. So if you ever wondered what the name of our galaxy was, you've heard the term before, but that is the actual name of our galaxy. And it contains over 400 billion stars. And all of these stars are held together by gravitational attraction. So our galaxy is more than just our 8 planets, or 9, if you consider Pluto still a planet, which I guess it's not at this point in time, but it's more than just those planets and our sun. It is an accumulation of over 400 billion stars, so it's a pretty large galaxy. But there are other galaxies that exist. It's not just our Milky Way. Space is super vast and expansive, and so the Milky Way is only one of over 1 billion galaxies that exist. So if you think about it, if the Milky Way has 400 billion stars in it, or over that, and the Milky Way is only one of 1 billion galaxies, and each of those galaxies have over 400 billion stars, it kind of like just blows your mind as to how big space is. And it's really even hard even now for me to wrap my brain around how big space is, and I can't even think about how large it is, because it's incredible, and it's never ending. Okay, so let's talk more about the Milky Way. So there's a few clusters that exist in the Milky Way. So we have galactic clusters and we have globular clusters. So our galactic clusters are very small groups of stars. So it's just small groupings of stars that we can talk about, maybe that create some sort of, Orion's Belt or the Big Dipper, little clusters like the Five Sisters. And then we also have globular stars, which are symmetrical, tightly packed clusters. And these can contain over 1 million stars or so. So they're larger, these globular clusters, but they are very tightly packed and very compact. So we have clusters that exist in the Milky Way, but the Milky Way does have 3 distinct parts, and you can see them over on this side of my screen here. So the first part here is a spherical concentration of stars at the center of the disk here, when you think about the Milky Way, and that's called the galactic nucleus. So the disk the disk is called the galactic nucleus here, and so the spherical concentration of stars is at the center of the disk. So the second part here, we have the rotating galactic disk, and that's containing very bright blue stars and also dust and gas. So we have that, which is kind of like the bright blue stars, but also the pieces of dust and dirt and space gas that exists between all of those stars as well. And then lastly here we have the spherical galactic halo. And this can contain over 150 globular clusters, which are the very symmetrical, tightly packed clusters that contains millions of stars. And so we have over 150 of those clusters, and that's forming kind of like a circular halo in the Milky Way. Okay, so we talked about the 3 parts of the Milky Way. So we know the Milky Way is our galaxy, right? So do we have neighbors? Well, yeah, I mean, there's thousands of millions of galaxies out there. So where is our nearest neighbor? Well, our nearest galaxy is a dwarf galaxy that is approximately 80,000 light years away from the solar system. So it's the closest one that we have, but it is a very small spherical galaxy. But the nearest galaxy that is the most similar in size and shape to our galaxy, the Milky Way, is what we have called or named Andromeda. So if you've heard of Andromeda, that is the nearest, most similar galaxy. So our galaxy is not a dwarf galaxy. Ours is larger, and so Andromeda is the most similar. But if you're talking about how far away it is 2 million light years away. So pretty far in comparison to the nearest dwarf galaxy that we have in our vastness of space that we're talking about. And so this is right here, this is an image of Andromeda. So this is the nearest one that looks the most like ours. Okay, so when we talk about galaxies, we have to mention Edwin Hubble. So Edwin Hubble was an American astronomer, and he was around from 1889 to 1953. And he was the one that developed the classification system for the structure of galaxies. And so he studied over 600 different galaxies and developed this classification scheme for the structure of them based on his findings. And so I think it's pretty cool that they named the Hubble telescope after him, because he did some significant work in regards to space. And so the current model of how galaxies are formed is based upon the Big Bang Theory, which I find ironic because they've also created a television series that's now over regarding the Big Bang and scientists and all that fun stuff. Obviously, it it has to do with, it's a sitcom, but I think it's ironic that they've named so many things after space and stars. Anyway, I digress. But anyway, back to Big Bang. So that's the theory on how galaxies are formed. That's our current model of ideas. So what actually is a Big Bang? So it's an explosive beginning, just like what the term sounds like. It's a big bang, it's an explosive beginning, and it's definitely got some oomph behind it. So the Big Bang Theory itself comes in 3 steps. And so step 1 is the expansion of the universe. And so that is what's happening first. The second step here is our background radiation step. And our third step is an abundance of elements. And so how did all of space and these galaxies form, right? So this is the theory, and based on the research of what has been done, is our most plausible option in explaining how our universe has been formed. So step 1, so the expansion of the universe. So remember Edwin Hubble, right? So he was the one that actually found a relationship between the nearest distance to a galaxy and the velocity at which it was moving away. So galaxies are moving, right? So different galaxies are moving at a certain speed or whatever, a certain velocity. So how far away is a galaxy, and how fast is it moving away? And this relationship is seen in all directions. So no matter which galaxy or which direction you're looking at, this is following true for this particular thing. And this is basically pointing back to a common beginning. So everything started, at a pinpoint, and now everything's moving away, right? And it's all moving at a certain velocity away based on how far away it is. And so you're looking at all of these relationships, and it can kind of point to a common starting point. So step 2 for the Big Bang Theory here is our background radiation, or our second theory, or proof of theory here. So when the Big Bang occurred, it occurred as an unstable form of energy. So obviously it started as energy. This energy itself is expanding and cooling, thus creating matter and space. And then the afterglow of what happened in the Big Bang is called our cosmic background radiation, which you can see an image of here. And so all of this cosmic background radiation was measured, and it agrees with the expanding model of the universe. So it agrees with the theory that the universe is expanding based on how much cosmic background radiation exists when they measured it. So this is another, I guess, step on proving the Big Bang Theory. And then the last step, or item of proof for the Big Bang Theory itself, is the abundance of elements that we have here. And so remember we talked about hydrogen atoms and helium nucleuses that exist in suns or stars? Well, the helium proportion itself should be approximately 24%. So in 2003, there were results from a probe, or the Wilkinson Microwave Anisotropy Probe, also known as WMAP or WMAP. So this showed a few different measurements. So there was a 1% margin of error when they did this study. So the remaining measurements here are outlined as follows. So 4% when they did this probe measured as ordinary matter. And then you have some questionables here. You have 23% as some sort of unknown type of dark matter, and 73% or so of a mysterious dark matter. And so after this particular probe did all of its measurements, we do see that there is ordinary matter that exists. So we do have helium in that ordinary matter, but we do have other unknown types of dark matter that exists in space as well. But we do have an abundance of these elements. We have a lot of dark matter. We have elements that exist in space. And so this is one of the third ways in proving or helping to try to prove the Big Bang theory. Okay, so we talked a little bit about galaxies. We talked about life cycles of a star. We talked about other various items of the universe. So how old is the universe? How old is the universe itself, which encompasses all of the galaxies and all of the stars? Well, we think that the universe is approximately 13.7 billion years old. So that's approximately when they think the universe had begun. And it's based on the fact that astronomers found the universe was not expanding at a constant rate. So originally they thought the universe was between, I believe, 10 and 20 billion years old. Essentially, astronomers found that the universe was not expanding at a constant rate. So it varied a little bit and made the lifespan of the universe a little bit shorter here. Also, the separation of galaxies is increasing. So this is being pushed by a mysterious force known as dark matter. So galaxies are separating at an increasing rate. And we don't know about this mysterious force known as dark energy. I think if I said dark matter, I meant dark energy. And we're not sure, but it is helping the galaxies start to separate. So what is the fate of the universe then? So what is happening? What will happen? So it will depend on the mass of the universe and if the expansion of the universe is either slowing or continuing. So is it going to continue expanding outward? Is it starting to slow down? Is it going to eventually stop expanding? So we don't know what's going to happen with the fate of the universe eventually. It does depend on those two things, depending on the mass and the rate of expansion. But luckily, I guess, we won't be here for the end of the universe, I guess. So that's a positive. But what I'm trying to say here is we don't know what will happen in this, and the galaxy, the universe itself it's pretty old, but depending on what's going to happen, the universe it depends on those two things, mass and expansion rate. So. Okay, so I think that's all that I have for today's class. Yep, exactly. So I just have those few slides, so hopefully I didn't go too long over my time. I tried to wrap it up pretty quickly and stay short, sweet, concise, and to the point, but make sure you're doing your reading. There are quite a few pages. That was a lot longer than the first session, the first part. You can read more about dark matter, people behind science, read more about dark energy in your book, but I just touched on it briefly. But make sure you're doing your readings, because if there is more information in the book on it, and then there is potential for it to be on your quiz. And so I will be returning for the next lecture and talking a little bit about the origin of the universe. And we're going to be covering more of that in depth, talking about the galaxy in regards to the spectral coloration. So until then, I'll see you guys here soon.